The main advantage of using an electric control valve with a STEPTOP actuator is that the STEPTOP eliminates the need for an air system as the pneumatic control valve power source. An electric control valve with a STEPTOP actuator also provides control performance equivalent to or better than a pneumatic control valve with a positioner. This video introduces common air systems and how electric control valves with STEPTOP actuators are revolutionizing the control valve industry. Let's get started. Pneumatic control valves require extremely clean instrument air with a low dew point. This system example shows a typical air system for producing such instrument air. Let's take a closer look at the equipment involved. 1. Here we have the air compressors. These devices use electric power to produce compressed air at about 1 megapascal. Air compressors are either positive displacement or dynamic devices. Either one or both types may be used in process industries. Commonly used compressors consume between 200 and 300 kilowatts of electricity per unit to produce 30 to 40 cubic meters of compressed air per minute, although devices vary depending on facility size. 2. Next is the aftercooler. When using an air compressor to compress air at 20 degrees Celsius to 1 megapascal or 10 atmospheres, the temperature theoretically rises to 293 degrees Celsius. This is known as adiabatic compression. This increased air temperature is brought back down to room temperature through heat exchange using cooling water. As the temperature decreases, however, the water in the compressed air collects in the bottom of the aftercooler. This water is then automatically discharged through the drain valve. 3. Here we see the air receiver tank. This pressure vessel suppresses fluctuations in pressure caused by changes in the amount of air used. Depending on the facility size and conditions, tank capacity can range from a few cubic meters to several dozen cubic meters. Moisture in the compressed air also collects in the bottom of the air receiver tank and is automatically discharged through the drain valve. 4. This device is the pre-filter. The built-in filter element removes airborne carbon particles and other dust particles contained in the compressed air being sent from the air compressor. 5. The compressed air then passes to the mist separator. Here, the internal filter element removes oil and water mist. 6. Next is the dryer. The dryer is used to remove even more moisture from the compressed air, lowering the dew point temperature of the air to about minus 40 degrees Celsius to prevent water droplets from forming on final control elements. The dryer shown here is a heatless dryer that uses some of the dry air being passed through the device to regenerate the desiccant in the dryer. The device is made up of 2 towers filled with a desiccant such as silica gel or activated alumina. The tower being used alternates every 8 hours, with the active tower drying the air while the desiccant in the inactive tower is regenerated. However, the desiccant must be replaced once every few years. 7. Here we have the afterfilter. This device removes desiccant and other foreign substances being sent from the dryer. There are generally 2 afterfilters installed in parallel toward the end of the air source system. The instrument air produced through this kind of system is compressed to between 0.5 and 0.6 megapascals and sent to pneumatic control valves at various locations inside the plant. As this example shows, air systems can be quite large and result in high installation costs. In addition to a significant amount of electricity being required for operation of the equipment, 5 to 10% of the compressed air will leak, resulting in lost energy. Equipment operation management, periodic replacement of absorbents and filter elements, and other high-maintenance work are also necessary. Using an electric control valve with a step-top actuator, however, eliminates the need for such an air system. There is also no need for complicated maintenance work. M-System step-top electric actuators introduced in this video are driven by a stepping motor. Using a step-top actuator enables smooth movement with a resolution well over 1/1000th, no overshoot movement, and no effects of the reaction force of fluid pressure, making it ideal for use with an electric control valve. Electric control valves with a step-top actuator also provide control performance equivalent to or better than pneumatic control valves with a positioner. This point is illustrated through comparative tests in a separate video, Revolution of Electric Control Valves, comparison between pneumatic control valve and electric control valve. Let's summarize that comparison next. A simulated plant facility, named Plantlet, is installed at the headquarters of M-System. This plant facility includes a flow control loop with a pneumatic control valve and an electric control valve with a step-top actuator installed in series on the same pipe. This is the pneumatic control valve. And this is the electric control valve with a step-top actuator. This flow diagram shows the Plantlet flow control loop. In this setup, either the pneumatic control valve or the electric control valve with a step-top actuator can be used with a single switch. By changing the set point value SP, we can use this control loop to compare the control results between the pneumatic control valve and the electric control valve. The results are then displayed in a trend graph. The results clearly show an advantage when using the electric control valve with a step-top actuator. For more information, please see the separate Revolution of Electric Control Valves video. The 1/1000th resolution demo kit with step-top for the Revolution of Electric Control Valves video, also available separately, provides a detailed look at the features of step-top electric actuators. This video is also recommended viewing. The era of air system-free control valves using step-top electric actuators has finally arrived. Thank you very much.